Alrighty, 11.6 is on the ratio and the root test. These are the last two tests that we're going to see, and I will be completely honest with you. The root test is far less important than the ratio test. The ratio test will show up everywhere. The root test, very, very seldom in my experience, okay? So let me first go ahead and show you what the ratio test is, what it says, and then we'll do a couple of examples so that we can actually sort of work it out, okay? Here is the ratio test. Okay? The ratio test, basically, if you have an a sub n, then you need to basically figure out what a sub n plus 1 is. So basically what the next term would be, just in the general form. And then you need to put them into a ratio and take the limit as n approaches infinity. And then you need to evaluate the answer. Okay? If it's less than 1, it converges. Okay? And converges absolutely. We'll discuss that here in a second. Diverges if it's greater than 1, or if it's greater than 1 as infinity, right? If it's a finite number greater than 1, or if it's an infinite number greater than 1, it diverges. But here's the real kicker. The ratio test is inconclusive, meaning that you need to use a different test, if the limit as n approaches infinity of that ratio is equal to 1. Okay? So let's go ahead. Oh, the whole absolute, at the beginning of this section, they talk about absolute versus conditional convergence. It's not that big of a deal. I actually don't usually cover it when I'm teaching calc. It's not, I don't think it's explicitly on the AP exam, and we'll come back and shore it up if indeed your teacher thinks it's important. But we're going to kind of skip over it right now. Just suffice it to say that anytime you see something that says absolutely convergent or converges absolutely, just translate it into your mind as converges, okay? So let's go ahead and let's do an easy one just to sort of warm us up. We have sigma n is equal to 1 to infinity of 1 over 2 to the n. Now that means that a sub n is 1 over 2 to the n. That means a sub n plus 1 is 1 over 2 to the n plus 1. That means the limit as n approaches infinity of 1 over 2 to the n plus 1 over 1 over 2 to the n is our ratio. That simplifies, and let's hope it simplifies, that's a complex fraction, me no likey, to that. Well, here's the thing. We understand that by rules of exponents, this becomes, in the denominator, 2 to the n times 2 to the first, right? So what happens here? Well, those cancel out, and I'm left with 1/2. Well, let's remind ourselves exactly what's going on here. If it is less than 1, it converges. Is this less than 1? Yes. So therefore, it converges by the ratio test. Okay? Let's go ahead and do another one. And we have 3 to the n over n factorial. Now, we need to ask ourselves, does this converge? I mean, it's always nice to get a sort of a hunch as to whether it converges before you even start the question. That way, if you get something really screwy, you have a chance to actually go back and perhaps fix a mistake. Now, we know the general relationship between the classes of functions and how fast they accelerate, right? This is an exponential. That is a pretty robust function. But factorials are more robust, okay? They increase faster than this does. And all you have to do is, 3, 9, 27, 81, 243, right? And then just keep going. But here's the thing. You have 1, 2, 6, 24, 120, And the next one's going to be 720. Now, this times 3 is, oh gosh, I don't even feel like doing that in my head. It's 729. Yeah, 729. 729. So it started out much lower. All of a sudden, this is catching up right here, okay? And so we need to ask ourselves what's really going on. Now, if we have 720 and we need to go ahead and get to the next factorial, that's 5040. Whereas the next multiple of, the next power of 3 is 2187. Started out lower, it remained lower, but it's actually accelerating faster. So the factorial is going to get much bigger, much faster. Okay, well that was a nice long, numerical segue or whatever explanation or demonstration that this is probably going to converge because the more powerful class of function is in the denominator. Well, we know that our a sub n is this, and therefore a sub n plus 1 is this. Okay? Well, that tells me that the limit as n approaches infinity, well, I know it's going to be a sub n over a sub, it's going to be this n plus 1 over the nth term. Okay, and let's go ahead and just, instead of putting it in a complex fraction, instead of dividing by it, let's multiply by its reciprocal. Okay, and what we're going to do, and actually, it is officially absolute value bars right here. And what happens here is 3 to the n cancels out with all but one of these 3's. I know that n plus 1 factorial is n plus 1 times n factorial when I simplify that, and we did that a couple of videos ago. So what I really have here is the limit as n approaches infinity of 3 over n plus 1. Well, I happen to know that that is going to be what? It's going to be 0. Is 0 less than 1? It certainly is, and therefore this converges by the ratio test. Okay, let's do another one. Like I said, this one really is going to be uber important because when we get to power series, we're actually going to use this. We're actually going to sort of tweak this a little bit and use it as a test for something else. So we have sigma 1 to infinity of n times 6/5 n. Well, I'm going to go out on a limb and say that this is probably going to diverge, since if the n wasn't there, it was going to diverge because it would be a geometric with a ratio greater than 1. With the n there, it's going to make it even worse. But let's go ahead and just for the sake of doing it and doing it right, let's go ahead and show analytically that this is indeed the case. Okay. So what I have here is I have the limit as n goes to infinity of n plus 1 times 6/5 to the n plus 1 over n times 6/5 to the n. Well, this cancels out with all but one of those, and I'm left with the limit as n goes to infinity of 6n plus 6 over 5n. Well, that's going to be 6/5. Well, 6/5 is greater than 1, therefore this diverges by the ratio test. Okay, well, let's do another one. How about ooh, what's that in the denominator? Well, remember that when we have something like f of x is equal to x to the x, that's not polynomial, because polynomial would be x to the n. That's not exponential, because that would be n to the x, right? It's neither of these. If I'm not mistaken, this is called a hyperfunction, but I could be wrong. But we still know that a sub n is n factorial over n to the nth. A sub n plus 1 is going to be n plus 1 factorial over n plus 1 to the n plus 1. If I have the limit as n approaches infinity of n plus 1 times n factorial, which is n plus 1 factorial, I'm just going to go ahead and get ahead of the game, and I have n plus 1 to the n times n plus 1. And of course, I've just reworked this a sub n plus 1. I've just simplified it a little bit. N to the n over n factorial. And we'll go ahead and put those in absolute value bars. Well, there's a little bit of canceling out that can go on here. This cancels with this. This cancels with this. And what I have here is I have the limit as n approaches infinity of n to the n over n plus 1 to the n. Well, we can use a little bit of rules of exponents, and we're going to have the limit as n approaches infinity of n over n plus 1 to the n. Well, let's see if we can change this and actually give ourselves anything. I know that this will always be a little bit less than 1 because the denominator is always going to be a little bit lower, okay? And so I know this is going to be 1 minus 1 over n plus 1 to the nth. Well, yeah, that doesn't really do much for me. I'm pretty sure that it's going to be greater, because that kind of looks like e. Pretty sure that that's going to wind up being more than 1. Yeah, give me a second. Actually, I'm pretty sure that that's actually some derivation of e, and therefore it's going to be greater than 1. But you know, basically, if you get down to something like this and you still have a problem, then perhaps do it by another means. Okay. Now, let's go ahead and move on to the next problem. Let's do n is equal to 0 to infinity of 5 to the n over 2 to the n plus 1. Now, we've seen this one before in a previous lecture. Let's see whether we can actually do this by the ratio test. So we have a sub n is equal to 5 to the n over 2 to the n plus 1, and a sub n plus 1 is 5 to the n plus 1 over 2 to the n plus 1 plus 1. So we have the limit as n approaches infinity of 5 to the n plus 1 over 2 to the n plus 1 plus 1 times 2 to the n plus 1 over 5 to the n. Okay. Now, here's the thing. This cancels out with all but one of those. Okay. Now, I'm pretty sure, since that's going to be very, very similar to 5 halves to the n, right? If I wanted to do it by comparison test or limit comparison test, 5 halves to the n would be the one that I would compare it to. But let's sort of bracket that for just a minute. And that certainly diverges, right? Let's go ahead and bracket that for just a moment, and we're going to wind up getting the limit as n approaches infinity of 5 times 2 to the n plus 1 over 2 to the n plus 1 plus 1. Well, guess what? As n goes to infinity, this becomes much less important. This becomes much less important. This ratio goes to 2 to the n over 2 to the n plus 1, or 1 half, and I get 5 halves. Well, 5 halves certainly diverges, okay? It is greater than 1, so it diverges by the ratio test. Okay? Now, that's pretty much an introduction to the ratio test. We'll go ahead and talk about the root test in the next lecture. The next video. So be prepared for that. As always, email me with any clarifications, questions, concerns, all that sort of fun stuff. Bye-bye.